Fluorescence lifetime imaging is known for short as FLIO. It's a novel clinical instrument for autofluorescence imaging that was developed by Heidelberg Engineering, and it provides unique high-contrast information on retinal fluorophores and their environment. Although it looks like a spectralis on the outside, the internal components are completely different. In this room, we're all familiar with the basics of fluorescence. When a compound absorbs a photon of light, it goes to a higher energy state, and within femtoseconds, it relaxes down to a more stable S1 state that eventually radiates in a picosecond time frame, radiates a new photon at a lower, at a longer wavelength, lower energy of light. When we detect fluorescence, there are multiple dimensions that we can detect it in. The first is the spectral dimension, where we see compounds have an absorption spectrum and then emit it at a longer wavelength. The second is the brightness dimension, shown on the second one, which is the common fluorescence imaging that we see on an autofluorescence image, where it measures the intensity of fluorescence coming back at each pixel. The new dimension is the lifetime dimension, where at each pixel we're actually looking at how fast the photons come back using a sophisticated photon counter. This allows us to start to distinguish between fluorophores and gives us much more information, as you can see here on this picture. If you're setting up a FLIO, there are a number of things that are different. First, instead of a continuous wave laser, you have to use a picosecond laser that is pulsed and sends a continuous train of pulses to the eye as it's scanned across the back of the eye. These photons are then collected, and instead of going to a diode, a CCD array, they go to photon detectors that actually count the photons and the timing of when they come back. And in these FLIO machine, it uses two different channels that it collects this. And then it creates an image, a color-coded image that shows the short lifetimes in red, and in the reddish colors, and the blue are the long lifetimes as they come back. This is a typical healthy eye with FLIO. The central reddish spot is the macular pigment. The orange-green background is the lipofusin, while the blue is the optic nerve and the vessels. If you compare that to a number of other pathologies, we see a wide range of different images, ranging from AMD and albinism, for example, which has no macular pigment, to MACTEL and retinitis pigmentosa and uveitis. We see many new patterns with this technology. And I'll go into these in a little more detail. For example, in MACTEL, macular telangiectasia type 2, it's very difficult for clinicians to make this diagnosis using conventional imaging, and it's often missed. With FLIO, we see a pathognomonic temporal crescent of long fluorescence lifetime decays over there that initially starts as a temporal crescent, and in more advanced diseases forms a circle around the fovea, making it much more easy to diagnose, monitor, and pick up subclinical cases. In age-related macular degeneration, we see much more than conventional imaging. We see long fluorescence lifetimes in the long channel that we see in almost every single AMD eye. And this is in areas that are clinically normal. And in fact, when we look at age-matched normals, 1/3 of them also show this unusual and unique image, unique finding. And we think that they may be at risk for future development of AMD. And in Stargardt disease, instead of just seeing the hyperfluorescent flecks, we can now start to distinguish between flecks. The reddish flecks are the newer ones and have short FLIO lifetimes, while the blue ones have longer lifetimes. And in the animation shown here, you can see flecks that we don't see on conventional imaging appearing initially in red and then changing to blue. So as we continue our work on FLIO, we're looking at many, many different diseases. AMD is a very important area where it can be useful, as well as MACTEL. We're looking at its role in uveitis. We see early changes that seem predictive of which patients are about to go into active phases of uveitis and could be targeted for further treatment. And we're also looking at potential for monitoring Plaquenil or hydroxychloroquine toxicity. And in our initial results, it seems to be every bit as good as current imaging or current detection technologies, and maybe even better. So in conclusion, FLIO is non-invasive and fast. It takes just 2 minutes. It is stable and reproducible and shows lifetime patterns in healthy eyes. These seem to change in early stages of different diseases, and these lifetime patterns are associated with disease and may be possible for early diagnosis. And it provides a new dimension in autofluorescence imaging that allows us to distinguish between various fluorophores that change early in the disease. And we're just now beginning the full potential of FLIO in ophthalmic imaging. And so at this point, I'd like to thank my team, and I think we will be seeing much more of this exciting technology. Thank you.